Good morning. I would like to welcome you all to the third sections of the first LNEC Lisbon Conference 2023 on flood, water scarcity and extreme events. Within this section, the topic is floods, and we'll have the opportunity to hear experts' view on key aspects for all types of floods, so coastal floods, river floods, urban floods, as well as those induced by man as dam break floods. This session will start with two keynotes and will be followed by a roundtable where experts will share knowledge on this important topic for researchers, technicians, water managers, and society in general. Our first keynote is lectured by André Fortunato, and is entitled Flooding of Estuarine Margins, Problem, Processes, and Predictions. So André is a civil engineering. He holds a PhD in environmental science and engineering and has an habilitation in maritime hydraulics. Nowadays, he is principal researcher at LNEC, where he has been a former head of the Estuaries and Coastal Zones Division. His domain of activity covers hydrodynamics, sediment dynamics, and water quality, with focus on hydrodynamics process in coastal zones, morphological evolution of coastal systems, development of operational systems, as well as development of numerical models and methods to simulate coastal processes. So, André, please.
Thank you, Teresa, for this nice introduction. Good morning, everyone, and thank you for being here this early in the morning. And I'd like to thank the organizers for giving me the opportunity to share some thoughts with you on floods. And in particular, I'll be talking about estuarine floods, their specific problems, the physical processes that are involved, and I'll share with you also some work that we've been doing over the past few years on the prediction of estuarine floods. So my outline is here. It will revolve around these three issues: the problems, the processes, and the predictions. First, I'll try to show you why we should care about the inundation of estuarine margins. Why is it a worthwhile problem to tackle? Then I'll talk about the physical processes and why they are different from both river and coastal processes. And then I'll discuss a little bit the issues around forecasting the inundation of estuarine margins. In the end, I'll wrap up with some my major messages. So when we talk about risks, and in this case, the risk of flooding of estuarine margins, it's convenient to separate the vulnerability and the hazard. Starting with the vulnerability, for me, it's clear that estuarine margins are extremely vulnerable, but I may be biased because I've been working in estuaries for all my life, my professional life at least. So I asked Bard and ChatGPT a few questions to try to show you why estuarine margins are vulnerable. And I was surprised to see different answers from Bard and from ChatGPT, and some of the answers were simply wrong. So my first message is don't trust ChatGPT too much, at least not for the moment. But, well, you still should use it, but you should be careful on how you use the answers. But still, I had some interesting ideas from my chat with ChatGPT. And if you look at the world in general, you'll find that many of the large cities in the world were developed around estuaries. You can take Tokyo, Shanghai, and São Paulo. These are 3 of the 5 major cities in the world, and they are in the margins of estuaries. If you look at Europe, you'll find London and Istanbul, which are 2 of the 3 largest cities in Europe, and then a lot of other cities like Hamburg and so on. If you look at Portugal, you'll find that the 3 largest cities, Lisbon, Oporto, and Vila Nova de Gaia, are also in the margins of estuaries. I was surprised with Vila Nova de Gaia. I wasn't aware it was the 3rd largest city in Portugal, but at least according to ChatGPT, it is. So anyway, It's clear that around large estuaries you tend to have large cities, so you have a lot of population, you have infrastructure, and you have economic activities in the margin of estuaries, so it's obvious that the vulnerability is high. Now, when you think about hazards, we should think about how climate change is increasing these hazards. The first issue, of course, is sea level rise. This is data from Cascais, which is in the coast near the Tagus estuary, and these dots represent monthly means of sea level. Then the red line is a quadratic regression, so it's clear that sea level is rising in Cascais, and it's rising at an increasing rate. The mean sea level was defined in Portugal in 1938 using this data, the data available at the time. So since then, the sea level has risen by about 20 centimeters. If you think about the future, we can look at the IPCC projection, the latest ones. You can see, well, the 20 centimeters that you could see at Cascais are represented here. This is the data, and these are the projections. So by the end of the 21st century, we're looking at projections of about 7 centimeters, 1 meter if we're if we are pessimistic. But of course, we expect the world not to end by the end of the 21st century, so we can easily extrapolate these curves and start thinking about sea level rises of the order of 1 or 2 meters. And of course, this will have a huge impact on the hazard in estuaries and coastal areas. The second issue associated to climate change that will increase the hazards in the coast and in the estuaries is the growing storminess, meaning more frequent and more intense storms. There is ample evidence of increasing storminess worldwide in many places in the world. So I thought I would share with you results from a very recent study. In this study, the authors simulated tides, mean sea level, and storm surges with a global ocean model. And they did the simulations for a period of 100 years, from 1950 to 2050. Then they compared the statistics of extreme water levels between the last 30 years of the simulation with the first 30 years of the simulation. And I'm showing you here results only for the storm surge component, so I'm not taking into account tides or the mean sea level. So this is the relative change in extreme storm level for a return period of 10 years between the last and the first 30 years of the simulation. The positive value in red represents a positive change, so an increase in the extreme levels, and a negative value represents a decrease in the extreme levels. So by and large, what you see are reds worldwide, which means that storminess will indeed increase in this period. However, if you look at our region, the Mediterranean region extending to the Iberian region, you actually see blues. So in this area, what is expected is actually that storminess will decrease. But thinking of the world as the world in general, we'll see an increase in storminess. Finally, we expect an increase in the variability of the river flow, which means that even in areas where the mean river flow decreases, the extremes could increase. I'm by no means an expert in this area, so I won't go into the details, but certainly you may remember the talk from Professor Trigo yesterday where he talked about this. So in summary, we have a problem, we have vulnerable areas, we have an hazard that is increasing, so this is a problem that we will have to tackle in the future. So let me now be more specific and give you a few examples for the specific case of the Tagus estuary. These are photographs from the margins of the estuary. The first two are from two rivers that discharge into the estuary, the Trancão and the Jamor Creek. Then we have several images from different areas of the estuary, Seixal, Alfeite, Alcochete, Lisbon itself, Seixal again. And the last one is from the coast. This is the overtopping of the seawalls during the Hercules storm that Celso Pinto showed yesterday. So, as you can see, this is a widespread problem that covers the whole estuary. You can see the dates, and you see that these are different dates, so it's a problem that occurs frequently. To be more detailed, I looked at the study from some of my colleagues, Ana Gil and Paulo Freire. So my colleagues built a geodatabase of inundations in the margins of the Tagus estuary. So these dots, these black dots, represent occurrences of inundations in the margins of the estuary. Based on this geodatabase, they estimated that the probability of occurrence of at least one inundation event in the margins of the Tagus estuary in any given year is 26%. So this is not a problem that occurs only now and then. This is a problem that we'll see again and again in our lifetimes. Of course, many of these events are relatively mild. They can correspond to road cuts or things like that, but occasionally we have significant problems. Here are two examples. The first one is what became known as the 1941 cyclone. This was a major storm that hit the Portuguese coast and created several problems in the Iberian Peninsula. You can see here a sunken ship. There were actually 150 ships that got sunk during this storm in the Tagus estuary alone. There were severe human casualties, 28 casualties, 14 injured. Many people had to be evacuated. More recently, in February 2010, there was a major storm called Xynthia. Xynthia followed more or less the same path as the 1941 cyclone. It then went on to France, where it killed tens of people in southern France, southwestern France. In Portugal, the problems were not so severe. There were no casualties, but there was extensive material damage, as you can see in these pictures. The dikes in the upstream part of the estuary were overflown 3 nights in a row. They were damaged. They had to be rebuilt and heightened due to the storm. So these events occur on a frequent basis, and occasionally they have large consequences. But so far I've only talked about the consequences to the margins of the estuary, but we'll have consequences inside the estuary as well. This is the upstream part of the Tagus estuary. You can see the bathymetry relative to mean sea level, and in orange you can see dikes. These dikes are very important because many of these areas are close to mean sea level or just slightly above. So without the dikes, they would be flooded at high tide. Let's now focus on this little island called Moção da Póvoa. This is the island in 2016. So you can see the dikes, you can see estuarine vegetation on the margins, and nothing looks strange here, except if you do a zoom here, you can see a small breach. It's a tiny breach, less than 10 meters wide, which lets water in and out at its tidal cycle. Well, the breach was small, but it kept growing, and this is the island in the last photograph available in Google Earth. This is April this year, and you see that the tiny breach is now not so tiny. It's longer than 250 meters, and the island's not really an island anymore. You can see that it's flooded. You can see channels forming on both sides, meaning that the water covers the whole island. So this is not really an island anymore. So the point I wanted to make with this is, if as a society we were unable to fix a small, tiny breach here, what will happen when sea level rises and we start having breaches all over the place, all over all these dikes? Will we be able to cope and to keep up with sea level as it rises and it starts destroying and overtopping all these dikes? Frankly, I don't think it will be possible to do so. So if this happens, some inundation may become permanent as the estuary reclaims what was formerly dry land protected by dikes. This will have enormous implications on the estuary. We'll have increasing salt intrusion, which will be aggravated by decreasing river flows, so all the biota will change. The tidal prism, which is the volume of water that goes in and out of the estuary during a tidal cycle, will increase, and we know that this will imply a change in the inlet cross-section, so we'll have a deepening of the cross-section. The residence times in the estuary will change, and this will affect water quality. So the impacts of sea level rise on the estuary will be dramatic, and we'll have to anticipate those changes so that we can take timely action. So I hope I have convinced you that the inundation of the estuarine margins is a problem and will have to be tackled. Let me now talk a little bit about the processes. The estuaries lie at the crossroads between rivers and oceans, so they are affected obviously by both ocean and river processes and also by atmospheric processes. The way all these processes interact can be highly nonlinear, so we should be careful in the way we approach this problem, because we cannot, if we try to oversimplify the problem, we'll run into major errors. And I'd like to show you a couple of examples of how these nonlinear interactions are important. My first example is for a study done in Delaware Bay in the United States. This is the domain we'll be looking at. This is the bay. We'll be looking at tidal elevations at 3 stations: Lewis, which is at the mouth of the bay, Reedy Point, which is in the middle, and then Philadelphia, which is closer to the head of the estuary. This is about 1 month long simulation, and during this month there were 2 extreme events: a storm surge here, that you can see in the 3 time series, and a river flood, which you can see primarily in the station upstream. Then these 2 columns show a blow-up of this graph during the storm surge and during the river flood. I'm not going to discuss all the results. I'm just going to discuss the results during the river flood. You can see the observations in black, and then 2 different simulations, the baseline simulation and the 3D barotropic simulation. So in the baseline simulation, we are simulating the whole, all the processes, including the effect of the density gradients. So the density gradients introduce horizontal forces and also stratification in the flow. In the 3D barotropic simulation, everything is similar except that we don't take density effects into account. And if you look, for instance, here, you'll see that there are significant differences between the baseline and the barotropic simulation. Clearly, the baseline simulation represents the water levels much better, and it shows that stratification can have a significant effect on the water levels. Basically, it reduces friction, so it reduces the dissipation of tidal energy in the estuary. So this is an example of how, in this case, the river flow and the tides interact to affect the extreme sea levels. A second example is in the interaction between the mean sea level and the tides. And this example is for the Tagus estuary again. The Tagus has an interesting characteristic, which is it has a resonance period of about 8 hours. This means that a wave with a period of 8 hours entering the estuary will reflect at the head of the estuary, and then the reflected wave will interact with the incoming wave, forming a partially standing wave that will lead to much higher water levels. Of course, the tide doesn't have an 8-hour period. It has a period of about 12 hours, but still semi-diurnal tides with a period of about 12 hours are still amplified by resonance inside the estuary. The consequence is that the amplitudes of the tides inside the Tagus estuary are much larger than the amplitudes outside the estuary. Now, when sea level rises, this will affect this amplification by resonance, and this will affect how the tides are changed by inside the estuary. So we cannot simply add the effect of sea level rise to the present tides and expect to obtain the future extreme sea levels in the Tagus estuary. The extreme sea levels will be higher than those that would be predicted if we simply added the mean sea level rise to the present tides. These are some results of a study in which we looked at this problem. So what you have here is the period of the incoming wave. So the tide will be somewhere around here. And this is the maximum amplification of the wave inside the estuary. The lower curve is the present situation of the present mean sea level. And you see that we have an amplification that can go up to about 65%. And for the tides, it will be, well, just below 60%. As the mean sea level rises, this amplification will actually increase. So the tidal amplitudes inside the Tagus estuary will increase with sea level rise. So these were just two examples. I'm going to show you some results from a more detailed study in which we looked at the dominant processes in storm surges in the Tagus estuary. So this is part of the domain that we modeled. That's the part we're going to be looking at the results. And we'll be looking at the results at these stations that are shown here in red throughout the estuary, from Carcavelos outside the estuary to Conchoso, well within the riverine portion of the domain. This graph shows the extreme surges at each of these points, each of these stations. So you see the stations here, and these black lines represent the maximum surge in each of these stations. We then try to separate the different effects in each of these stations. So you're looking at the effects of local waves, river flow, atmospheric pressure inside the domain, the wind inside the domain, the waves at the boundary. So I'm talking about, in this case, sea waves that enter the domain at the ocean boundary, and then the surge also at the ocean boundary, which is this surge being caused primarily by low atmospheric pressures. So if we now look at the results, here are the main conclusions. And the ocean surge plays a very important role, and it propagates far into the river. You see this light blue column means that we have the effect of the surge can be of the order of half a meter, even at Conchoso, which is really far into the river. The effect of the ocean waves is also very important, can be well over half a meter at the coast, and it does propagate also inside the estuary, and it is non-negligible even at the riverine portion of the domain. So this was a somewhat surprising effect for a result for us, because of course we expected the ocean waves to play a major role in the extreme water levels at the coast, but we did not expect, especially in such a large estuary, to see the impact of waves to propagate far into the river. The local winds can be important in shallow and wide regions. That's this area right here. Of course, the wider the estuary, the more the effect of wind will be. And also, the shallower the region, also the more important this effect will be. The effect of the river flow is important in the upstream part, but then as the estuary widens, this effect in green here basically disappears. The effect of the local waves is relatively negligible, even though it's such a wide estuary. So these were our main conclusions, and one of the take-home messages here is that the Portuguese legislation on inundations should be reviewed, because this legislation indicates what are the effects that should be taken into account in these studies, and they specifically mention taking into account the local waves, and they specifically neglect the waves at the boundaries, and as you can see from these results, it's exactly the opposite that we should be doing. So I've talked about the processes. Let me move on to the last part of my talk, the forecast of estuary inundations. We are all familiar with large-scale predictions. We routinely use large-scale prediction coming from Met offices everywhere, NOAA from ECMWF, IPMA in Portugal, and so on. So These forecasts are now common. They are relatively accurate. We have forecasts for waves, tides, storm surges, and so on. They are produced a few days in advance, and they are now used for civil protection, harbor operation, and so on. They are fairly accurate. There was a recent study that analyzed the forecasts from Copernicus, and it concluded that the peak water levels in European coasts were predicted with a 10% under prediction. So there is room for improvement, but for many practical purposes, the forecasts that we have are perfectly decent. But this is large scale. At estuarine scale, so at local scales, things are a bit different. These projects that are produced by national and supranational organizations, they are often unsuited for small estuarine scales and for inundation. The requirements for this prediction are much more stringent. The physical processes are more complex. For instance, we may have to take into account wave current interactions, wetting and drying, and so on. The bathymetry is much more important, and the bathymetry is usually unavailable in large public repositories. The bathymetry changes due to dredging or to natural processes. We need much higher spatial resolution to resolve small features like dikes or narrow channels. Also, the output requirements may vary widely for different users. So what we've been advocating is the need for decentralized forecast systems to address these local estuarine scales. Of course, this is not an easy problem, and what we have developed over the past few years to try to address this problem is a platform called Open Coasts. Open Coasts is a web portal that lets users assemble on-demand coastal forecast system for any coastal system of their choice. So with Open Coasts, the end user can generate daily forecasts of water levels, wave parameters, velocities, salinities, temperatures, water quality variables, and so on. So Open Coasts is based on a sophisticated numerical model, Schism, and it offers services to deploy the forecasts, to manage them, and then to visualize and download the results. We have been offering courses on Open Coasts worldwide, from Europe to Asia to Africa and to America, and we have found that even users with a very limited background in modeling can rapidly learn how to create a forecast deployment. The major difficulty was providing a grid, because we ask users to provide a grid for their system of choice, and this is by no means straightforward to generate and to provide. So a couple of weeks ago, we included a grid generator inside Open Coasts so that the users can generate their own grid and then provide this grid to Open Coasts to create their own forecasts. So here's a quick example of a forecast system for the Tagus estuary. You can see these are the outputs in Open Coasts. You can see a map of instantaneous elevation right here. You can see time series of water levels in Cascais and Vilafranca de Xira. And you can actually recognize the resonance effect that I was talking about a few slides ago, where you see how the tidal amplitude in Vilafranca is so much larger than at Cascais. So I'm just over my time. Let me wrap up by summarizing the key messages. Regarding the problems, I hope to have convinced you that estuarine margins are vulnerable because many large cities grow around the large estuaries, and that the hazard will keep on increasing due to climate change. I also tried to show you that many estuaries will experience dramatic changes associated to sea level rise and the associated inundations related to sea level rise. Regarding the processes, I showed you that estuarine water levels are determined by fluvial processes, ocean, and atmospheric processes. The interaction between these different forcings can be highly nonlinear, so we should avoid the temptation of oversimplifying the problem. We also found that there are some changes that should be made to the Portuguese legislation because the processes that are recommended are not the the major drivers are not taken into account. Finally, regarding the predictions, we now have large-scale ocean forecasts available, produced by several institutions, but we believe that small-scale estuarine processes should be performed by local institutions like universities, harbors, water management institutions, and so on. This can be done with open codes, which empowers the users to generate their own forecast system, and it can also be a key component of digital twins that will be developed in the near future. Finally, simplifying the generation of forecasts can pave the way to have several forecasts for the same place, and therefore enabling ensemble predictions which can improve accuracy and reduce uncertainty. So thanks a lot for your attention. I'd like to acknowledge the many collaborators whose work I've shown here, and also the institutions that funded the projects for which I showed you results. Thank you.
Thank you very much, André, for this great keynote on estuarine floods. So now we have time for some questions, 1 or 2 questions. Lobo Ferreira, please. João Paulo.
Thank you, André. Thank you, André. It was very interesting. We had worked also in Aveiro, your side on what you saw, the estuary, and we on groundwater, and trying to see the irreversible consequences on inland water when you have the surge, the storms, etc. But I was willing to ask you just one question, and this more or less the geological timing compared to mankind timing. If I'm not wrong, from the last 11,000 years, during the warm period, the sea level in 11,000 years, you have Jericho 8,000 years, so the mankind was already there in civilization, was rising 120 meters, because it was the warm period with the ice caps. Scandinavian Peninsula these days is still going up, okay, because the glaciers that were there melting, and it takes a long time. So during this time, I think when you see with the zoom our time scale, it seems that something is not comparing to the other causes. So if you have 120 meters rise in 10,000 years due to different types of approach, now we are taking care about 2 centimeters, or if the melting of the Greenland glaciers will come above 2 meters. I was just saying, scientists saying in Greenland that probably by the end of the century it's 2 meters. But what is the scale compared to what we're seeing now? I've just been in Miami, everything is on the floor, so if you rise half a meter, it's going to be flooded. How do we tackle with the geological times and what is happening? I was seeing in Caesarea in Israel that it was under the sea, or Alexandria, but the other parts are rising up. So you have different types of parameters. If you compare, it's suffering, the mankind is changing, but the geological times also show that we are considering the world to be a fixed. We have a photo, but it's a video, it's changing. What do you think about that?
Well, really, I'm not very concerned. I'm an engineer, I'm not a geologist. I'm not very concerned with geological timescales. I mean, if the sea level was rising in the past when the population was very small, it was easy to relocate, and so I don't think it was a problem. And also, you talk about 120 meters, but that was during a very large period. So the speed at which the sea level is rising is what causes the major problem, right? So the time we have to adapt is small, and that's why I think that the coastal managers are now planning, taking into account the fact that sea level is rising. So if they wait for the sea level to rise to start taking action, it will be too late and too costly.
Okay, yeah, there, another question, please.
Yeah, thank you. That was really very nicely put, the last phrase you did, and also your presentation. Thanks a lot. For me, it reconfirms really what I said yesterday. On European level, we need to move the Water Framework Directive and the Marine Strategy Framework Directive closer together, trying to harmonize the two. You seem to confirm that on Portuguese level. Obviously, we have a problem. I mean, and you have very nice forecasting systems. I'm quite keen to get to know better your open coast modeling framework. In Italy, in the Po River Delta, I mean, we repeatedly had inflow of marine water 30 kilometers inland, which really shifted whole ecosystems, and on top of it also has a huge impact on agriculture, so food security in a way. So we know there is a big problem. Do you have any comment on possible solutions, perhaps? I mean, how can we tackle this huge problem, which is a European problem, really? Thank you.
Well, it's not a European problem, it's a world problem, and actually there are parts of the world which are worse than we are. Well, João Paulo was just talking about Florida, where they do have problems, and if you think of places like Bangladesh, they are obviously much worse than we are. Solutions. Well, I really don't see any other solution than to retreat. We cannot hold the sea with our hands. We could think of holding the sea at very, very localized places, but it's going to be so overwhelming that I don't see any other way but to retreat. And the sooner we start doing it, the better.
Okay. Does anyone have one more question, please? No? Okay. É o Rui, não é? Rui.
Thank you. You have mentioned that the Portuguese legislation should be reviewed in order to take into account the phenomenon you have taken in the estuary, in the Portuguese estuary, namely the fact that the waves could contribute to the results we got. Have you looked to other legislation, namely European legislation or other countries?
No, specifically we were doing a contract to the municipality of Vila Franca de Xira. We were building inundation maps, and we were asked to follow the specific legislation. So of course we had to look at the legislation, and we had to make sure that that the approach that we followed agreed with the legislation. And what we found was that we had to include processes that were not explicitly mentioned in the legislation, and that some of the processes that the legislation told us we should take into account, of course we did, but they were not that important. But so the answer to your question is no, we did not look at other legislation because this was the one that we had to follow.
Okay, I think we can move on for the next keynote. So the second keynote is lectured by José Pedro Matos and is entitled In Search of the Risk Associated with Dam Failures, a tale of efficient computing and method modeling to implement an integrated probabilistic framework. José Pedro obtained his Master of Science at Instituto Superior Técnico of the Lisbon University. He holds a PhD at École Polytechnique de Lausanne, and he has worked in EPFL as a postdoc, in Granarstaki as deputy head of department, leader of the Competence Center for Hydrology and team leader for hydraulics and hydrology of dams, of important dams projects. Nowadays, he is an assistant professor in the Instituto Superior Técnico. His domain of activity covers water resources management and hydrology, operational probabilistic forecasting, uncertainty and risk, machine learning and large-scale hydrology, as well as optimization and operation of complex hydropower systems. So please.
Thank you very much. It is a huge honor to be here within these walls and speaking to this distinguished audience. As you can see, the lesser the CV, the longest the description. But thank you very much. It was very flattering. So I will talk about risk associated with dam failures, which is something I studied and then worked in. I'll just start the chronometer, not to take too much of your time. So why risk associated with dams? Why risk in general? So on the left, you have Banqiao Dam. After its collapse in the 70s, it was a dam in China. It collapsed due to very intense floods during a typhoon. Estimates indicate that about 230,000 people died directly and indirectly because of this failure. Here you have Vaillant Dam. If I'm not mistaken, it was at the time of construction the highest dam in the world. It's in the Dolomiti, in the north of Italy. The engineers knew that Mount Stock on the side slope of the reservoir was sliding down. They thought they could control the speeds of this descent. They couldn't. Most of them died, actually, when a 200-meter wave overtopped the dam and killed 2,000 people downstream in the valley. So dams are super dangerous. They can really kill a lot of people and bring a huge amount of destruction. We are super concerned about nuclear power plants, for example. If a dam fails, it can be much, much worse. So fortunately, dams are really built not to fail. The idea is that the design is based on deterministic cases. So we design large dams to be able to cope with the probable maximum flood, with the maximum credible earthquake. And this means that the risk associated, for example, with the design flood is the probability of the design flood, which is very small, times the loss, and this equals 0. Otherwise, we would not build a dam at all. But so risk is part of the design, but not really at the same time, because risk is really the integral of all the floods, all the conditions, all the flood peaks, all the volumes, all the evacuation, all the communication, all the hydromechanical equipment that may work or may not. And then the risk is the integral of all these things, and we don't know what it is usually when we build a dam. So in reality, the risk associated with the dam is the integral of the probability of failure times the loss associated with each failure. And this is something hopefully very small. And I have to say it works quite well, because we don't have that many large dam failures. But still, there's of course an interest in knowing what is the true risk associated with a large dam, and then understand what are the things that contribute the most to this risk. Here on the right, you see an FN curve. So here you have the cumulative frequency of an event, and here on the x-axis you have the lives lost due to this event. And if we are here, we are at unacceptable risk, because the probability of losing many lives in a given year is very high. And on the lower left corner, we are in a zone of acceptable risk, because the probability of losing even a few lives is very, very, very small. So a design criteria may be, for example, a flood or an earthquake that kills an estimated 100 people with a probability or with a return period of 100,000 years, which is reasonable. And the risk associated with this would be 0.001 deaths per year. But then we can think about the integration of this. So if we are unlucky, so with a lower probability, maybe the evacuation doesn't go well, maybe something is wrong that we didn't anticipate, and a few more people die. With a lesser probability, but still this can happen. So if we integrate this risk, we are increasing from 0.001 almost twofold. So now it's 0.023. And maybe we are lucky, but still we have a big event, so we add another, we double again the risk. And if we integrate all of this, we have a total risk that is 7 times higher than the risk associated with the design event. So maybe 7 times is not very important because we are talking about very low risks, but still I would say it's worth quantifying and it's worth understanding. So I'm an hydrologist, and for me, uncertainty is everywhere. I'm thinking about uncertainty all the time. I work a lot in operational forecasting with meteorological predictions, and really it's impossible to have it right. We always think about a framework, an interval of things that may happen over the next few days. So I find that in dam design, uncertainty is just politely ignored sometimes. And there are good and bad reasons to do this. So often, uncertainty is ignored because it's just not relevant. Some processes we understand so well that we have pushed through our understanding, through our models, uncertainty to a very small degree. And then it's fine to use deterministic approaches. Then there is a middle of the road reason not to use uncertainty. Maybe it's just too difficult. For a given project, maybe I need too much data, maybe I need too much time, and it's just not feasible to look at uncertainty with proper eyes, let's say, as we'd say in Portuguese. And then there is a very bad reason, which is that historically we couldn't do it, so because of inertia we continue not doing it. I really think we should not be afraid of exploring this probabilistic way of thinking about risk. So now, my impression is that we should look at uncertainty, we should look at integrated risk, and then how to do it, because it's really complex. So the probability of a dam failure occurring has mainly to do with the dam reservoir system. Many things affect the system. Examples are floods, earthquakes, internal erosion, failures in the equipment, communication failures, etc. And then there are elements in the dam that play in a dynamical way with the reservoir. And if we model this, if we understand this, we can have a probability of failure and also a history of the failure, the conditions of the failure. And then we have the downstream area. To understand what happens in the downstream area, we need to look at the dam break wave. And then we need to consider that most of the losses are not in the dam, they are downstream. Environmental losses, infrastructure, houses, and lives. So, starting with the failure. Now this is an exercise, a proof of concept of how we can really study an integrated risk model. Before doing it, I was part of my life, years of my life were dedicated to the construction of the Rogun Dam. This will be the highest dam in the world in Tajikistan. Here you see a picture of the upstream part of the dam while it's being filled. It has many, many problems. So it's a highly seismic zone. I felt a strong earthquake while I was there, so I could experience it. The river is called the Vash River. It is, in the local dialect, they told me it means savage or wild. So you have this issue with floods. But earthquakes and floods are not the worst that affects this dam. It's over an active salt wedge that can dissolve in one day. It has a huge sedimentation, so the amount of sediments that come into the reservoir at the peak yearly flood is 10 tons per second. So during construction, we had to build really fast to overcome these challenges, mainly the salt wedge and the sedimentation. Now it's okay, but at some point, the contractor was trying to explore some alternatives to speed up the project. And we did this kind of tree analysis for a large dam, and our goal was to tell the contractor, to show to the contractor, really this is too dangerous, we shouldn't do it. And I was doing the math on this, and of course we brought in experts from other places. And my feeling after doing this was that it's very subjective. You need to exercise a lot of imagination to think about all the scenarios that can lead to failure, and then you need to put probabilities into all of these links. And you get a nice picture of the risk, but it's not integrated. So this is another approach, a dynamic link which considers many, many hazards at once, and then feedback loops, so aftershocks, wet years where you have increased probability of floods, one after the other, levels in the reservoir, epistemic and aleatoric uncertainty, both kinds of uncertainty, and also element characterization using fragility instead of vulnerability. So in a given action, for example, a PGA, peak ground acceleration, my component may break or not, depending on how lucky I am. So we factored all of this into the simulation, and we simulated millions of years. And this takes up a lot of computational resources. So we used the generic multi-risk approach, which was proposed by Arnaud Mignon, a colleague from Zurich. And the idea is basically that you sample primary triggers, triggering events, and if no trigger event happens, you just skip the year. If a trigger event happens, maybe an earthquake or a flood, then you simulate in detail all the year after this trigger event. And then you get thousands or hundreds or thousands of full histories of a failure or not. So this is one example. We got many of these. So that's the level of the reservoir, and then an earthquake happened, and a drawdown was started. There was some damage to the discharge capacity, but then the system recovered, and finally the reservoir was drawn down successfully. No problem there. This is another example. This one led to failure. We have an earthquake with a return period of 12,000 years, some damage. They succeed in drawing down the reservoir, but then there is another earthquake, smaller, return period of 3,200 years, and then they lose the capacity to release water. The yearly flood comes, and the dam is overtopped. We had hundreds of these. So we really could understand the risk of failure and what led to failure in an integrated way. So for each failure, the idea was to simulate the 100 kilometers of valley downstream. And this, of course, takes many hours, each simulation. And for hundreds of failures, it was impossible to do it. So we had no time, no computational resources. So, and also something I forgot to tell you. So there's a failure, but the reservoir may not be full. Right? Maybe it's half full when it fails, so you release less water. And then the breach, we know from the work of Fröhlich, it's not deterministic as well. Sometimes it progresses more rapidly, sometimes more slowly. So we simulated thousands of possible outflow hydrographs from this dam. And that's maybe the first interesting idea. We looked at cluster analysis and the amount of variability lost. And out of these, mathematically, we selected a group of a number of simulations to maximize the variability of what we were simulating. So we selected a library of dam break waves to simulate. And with this library, we applied meta-modeling with machine learning so that we could, from the characteristics of the outflow hydrograph, we could estimate inundation parameters in all the domain very quickly, based on this portfolio of simulations. So we were estimating very fast, based on these portfolio, peak velocities, peak elevations, and peak and time of arrival. And we could we could have an estimation of the flooding in the valley for thousands of failures. And then we come to the losses. So we have two kinds of losses: tangible losses, so the ones you can easily measure with money, so infrastructure, houses, etc. And then we have intangible losses with loss of life, that are associated with loss of life. And the data we had were very nice. We had the footprint of every building, the typology of the construction. So we crossed this information with data from tsunamis. And we could estimate for each individual building the probability of stuff happening. Here you see a map of the probability or the return period of the building being collapsed or worse as a consequence of the dam failure upstream. So a very fine-grained analysis. And with this, we could perform an FN curve analysis. Here you see the cumulative frequency of losses and the volume of construction collapsed or washed away. We could do the same for infrastructure, etc. So a very nice depiction of risk. I will try now to show you a small animation for the intangible losses. So for the intangible losses, it was a fun work to do, because we could simulate with this MATSIM model from ETHZ as well, the evacuation of the flood area. So what you see here, the white dots are people fleeing. They go to the mountains, they get out of the zone, and then the flood arrives. So we could actually get the results of the crossing between thousands of inundation waves and thousands of evacuation exercises to get an estimate of how many people would die as a consequence of all the failures. Yeah, so it's really, really nice, the data. So we have to be thankful for this. So back to the presentation. Yeah. So findings. Back to the importance of uncertainty. We use this to study 3 cases. So the reference case with aleatoric uncertainty and vulnerability. So the usual case, I would say. Then reference case plus epistemic uncertainty, what we don't know about the hazards. And then reference case plus epistemic uncertainty plus fragility. So we can be lucky with the response of the elements. Maybe with a certain wave velocity, the building does not collapse. In some other cases, it will collapse. And we considered all of this. So here you have vulnerability. So past a certain return period of the event, the building collapses or the element collapses. And here you have fragility. So you have different probabilities of different things happening to the building. So we threw all of this in the analysis, and you see 2 things. First, the return period of the failure decreases as you consider more and more uncertainty. It starts at 80,000 years in this exercise. It drops down to 20,000 years, which is fine. But more interesting is what happens to the risk profile. So the reference case is there. So you have damage, you have loss with high return periods. And when you put especially fragility, it really, really reduces. So you can have events that are much more likely. Normally they would not lead to any loss. But if you are unlucky, they can lead to loss. And this is really important in the overall risk profile. And I was thinking a lot about this, because really I was not expecting that such low return periods, events, would lead to failures. And finally, what I discovered was quite simple, is that pessimists had it right all along. Because this is a log scale with return periods, for a given event, you have more chances of being unlucky than of being lucky. So you're lucky when the return period is higher. You expect it to fail, but it doesn't fail. And you're unlucky when the return period is lower. You expect it to stand in place, but it doesn't. But because the return period is not linear, you get much more opportunities to being having bad luck than opportunities to being happy. And that's really the reason why accounting for fragility and uncertainty can alter the risk profile and is very important. So, epilogue. Some considerations for the roundtable and some things that worry me in general when I think about risk. First thing, black swans. I imagine many of you have heard about black swans. So I had read the book years ago, before starting even the PhD. It's a very interesting book by Nassim Nicholas Taleb. And the concept is basically the following. Some events are impossible to predict. And the black swan is an allegory, a useful one, because all swans were white. So we traveled to China and swans were white. We traveled to other places and swans were white. And every time we saw another white swan, our belief that all swans were white was reinforced. Until Captain Cook arrived in Australia and there were black swans. So this would be impossible to predict. But of course you can do it with hindsight, you know. But if I tell you there are blue swans, you'll think I'm crazy. It's a bit the same. So the idea is that some events are just impossible to predict. And some years ago, I was in this big project meeting with a lot of smart people, and they were all talking about being able to predict black swans. And I was young, I had read the book, and I didn't say anything, but I was thinking, you missed the point entirely. The whole concept of a black swan is that you cannot predict it. So we should get used to it. Some things we cannot predict. Something else, risk is part of life. There are 412 nuclear reactors in the world. If we designed all of them, each one of them, for a 10,000-year return period, what would be the failure rate? 1 every 25 years. Fortunately, I think we do it for a little more than 10,000 years. But still, I mean, we should expect that some of them fail. There are more than 57,000 large dams in the world. I mean, of course some dams will fail. It's just mathematics. Every time a dam fails, we are very shocked, we blame climate change, etc. I mean, certainly each failure has a history, each failure has reasons, each failure could be avoided, but maths tells us failures are bound to happen. So, in this, Rodrigo, he said yesterday that designing for resilience was important, and I fully agree. This is why designing for probable maximum flood and maximum credible earthquake are very good ideas in this kind of critical infrastructures. So we go beyond return period. Something else, there is no such thing as a free lunch. This is a rock curve, which I really love to think about decision making. So the rock curve shows you the true positive rate and the false positive rate of any binary decision. So imagine there is a flood. You got some kind of forecast from IPMA. And what you want your forecast to be there. So you want true positive rate. Every time there is a flood, you are able to predict it. So 100% of the time. And at the same time, what you want is a zero false positive rate. You don't want to issue a flood warning, and then there is no flood. It's a nuisance. It's very easy to get all the floods right. I just issue a warning every day. It's also very easy to get the zero positive rate. I never issue a warning. In reality, we are bound to these curves. So a better model, maybe ECMWF, will get you here. A worse model, maybe GFS, will get you here. But to get the high true positive rate, we for sure need very high false positive rates. So we should know this. We should decide this previously. And it's very hard. For example, for a dam. You know that something is going to happen. You should draw down the reservoir. But this is very expensive. You lose water. Maybe you start flooding, a mild flooding downstream. Who is going to make this decision? And then who's going to make this decision at 2 a.m. on a Saturday without speaking to everyone around? Very, very hard. I think we really should consider the decisions before the events take place. 2021 floods in Central Europe. Yesterday, there was a talk that mentioned what happened in Germany. I was tangentially involved with the forensic analysis of what happened in Belgium. So you see Europe's deadly floods leave scientists stunned, and the floods, where 39 people died in Wallonia, were caused by a very intense precipitation in a station called Jaillet of 300 millimeters in 72 hours, if my memory serves me well. And here you can see the forecast, what happened. So, I'm sorry, this is what happened. So you have a very intense precipitation here. I'm tired. This is the difference between the forecast and what happened. This is what I wanted to say. So here you have a very positive, and here you have negative. So the models, they were predicting a large rainfall in Germany, and finally it happened some kilometers away in Belgium. So people were not prepared. And if we look at the ECMWF's ensemble, it passed 200 millimeters in the same time frame. So it was not unexpected in a way that a large flood could happen there. But you have a huge uncertainty. Will you start drawing down? Maybe 1 week in advance? But it's not so easy. This is what happened in the dam that caused the flooding. So the level was going up, inflows were going up, that at some point they go down. And there is a huge, huge peak when the dam is already almost full. And of course, the most important is that the dam doesn't fail. So the operator, I did not talk to him, but he talked to my colleagues. He was crying, describing what happened this night, and saying that he knew he would kill people, but still he had to open the bottom outlet to save the dam. And this is super sad. And it's very hard to handle uncertainty and risk. And when you do the math, the whole flood could be stored in the volume of the reservoir if they started emptying 1 week earlier. But it's just very hard to do. Here is the uncertainty analysis. This is a generalized extreme value distribution with the data pre-flood. So you have this. And the flood was there, almost 300 millimeters. And according to the analysis, well, it's an event with a return period of more than 1,000 years. But these are uncertainty bands. And this means that with a 5% chance, the true return period of the event is 80 years, could be 80 years. So this is what uncertainty means. Uncertainty means we don't know. We decide based on the middle range, but maybe 39 people died because the dam had to release water for an event with a return period of 80 years. 80 years, it's not enough for a dam to fail. It's much too low. And really, uncertainty means we don't know. We should have this in mind. And again, it's maybe a good idea to over-design. And of course, we blame climate change. It's the usual culprit. And climate change will be a tremendous challenge, but it's not the culprit for everything that happens. Libya, floods. The flood response that increased their death toll. Here's something else. So in the BBC, I found this article, and then there is a researcher that says, I looked at the dam, and I showed it had fragility, and it would not be able to cope with a large flood. But imagine you're in an impoverished country, very dry country. There is some guy telling you there are security problems, issues with the dam. Will you draw it down? Will you cause huge economical collapse? Drought? Agriculture that needs to stop? It's a very hard decision to make. And coming to the end, it takes real courage to act in these events. This is Roger Boisjoli. Maybe you know of him. You certainly remember the Challenge space shuttle disaster in 1986, where the space shuttle blew up. And he was working for a subcontractor of NASA. And they had an impressive portfolio of all the items, all the pieces of the space shuttle. And In this particular launch, due to bad weather, it had been delayed, I think, 2 times already. And NASA really wanted to launch it this time, in spite of the cold. And this engineer, larger-than-life personality, super serious and committed, he tells them, look, these O-rings in particular that are under my supervision, they have never been tested for such low temperatures. For me, it's a no-go. And then NASA talks to his company, and his boss talks to him, sign it. And he goes, I won't sign it. You do if you want to. And his boss signed it. And it blew up. This story is bad for the people there. It's good for him. He was the hero. But normally, you're not sure that the disaster is going to happen. Maybe the probability of disaster is 0.01, 1 in 100. So if you really put your foot down, and you say, I won't sign, the most likely outcome is that you're the idiot. You didn't do it. You're shunned by your peers. You're fired out of the company. And nothing happens in the end. That's just probability. So in case of low probability high consequence events, especially when you don't suffer the consequence, it's a rational decision not to sound the alarm. It's the best thing for you. And really the way out of this, I've thought about this a lot, is really professionalist versus personal interest. It's not even about corruption, it's just mathematics. For you, you're put in a position when the most logical thing is to do nothing, is to keep quiet. So we really need to be professional. We really need to be brave, stick to our guns, and behave as very responsible engineers. Not easy. Thank you very much.
Thank you, José Pedro, for this excellent keynote on dam break floods. We are running out of time, but still I would like to have one or two questions to José Pedro.
Yeah, Jose, really fascinating, absolutely great. I really enjoyed it. Actually, I'm not very prepared for the question I will ask. I will have to think about your presentation, which was very rich. I think it's not about engineers only, it's really a core point, the responsibility of scientists when advising policy making, decision making. I was thinking when you talked about the earthquake in the Abruzzen quite some years ago, that some scientists had said just before a major earthquake happened, go home, drink your red wine, and then the same people who went home and drank the red wine, they lost their homes and their lives partly. And some of these scientists were actually taken to court, which was quite unique in Europe. It happens in the US, but hardly ever in Europe. And this raises a huge question about us as scientists. What is really our role? How do we formulate our messages when we provide advice? Similarly, I was thinking of the Vargin Dam in the 60s, who led to a major disaster in the north of Italy. There also were warnings. Maybe I'm in just now because I will go back again to your great presentation. I think you were too much focused on the individual. I think the important point is here, we need to work together in committees. Actually, it's never, ever, in my opinion, a policymaker, politician should listen to one scientist, because let's face it, we are human beings. We are, of course, biased. I mean, the best scientists, we try to be neutral, we try to be objective, but due to our education, our background, due to the way and the colleagues we interact, we have a bias. So ideally, there should be committees working together. Uncertainties should be transparently communicated. That's a huge difficulty and challenge to us, because politicians are averse to it. They don't like any gray zones in curves. They like a clear line, one dot maybe, and this is something you have to focus on. Anyway, just to stimulate, I hope we will discuss it, or maybe you there now in the roundtable, really great, thanks a lot, and a difficult topic, which we should elaborate on. Thank you.
Thank you. I'm not sure what the question was, but I agree with 100% with what you said. I think committees, they really help. I mean, if you're doing it as a team, then it's much easier to tell the decision makers or to force maybe a contractor or an owner of a project to stop. But sometimes there is so much pressure, and sometimes you're the expert within the group that needs to sound the alarm. And then when things get difficult. Also, with climate change, it's very easy to sound the alarm because we have nothing to pay for it. We say, we should do the transition, but we don't care about who's paying. We don't care about who will be damaged. That's easy to do. But if the people affected are across the room from you, and if they are more powerful than you, if they employ you, then it's really hard. And they ask you, okay, so you want me to draw down this multi-million-dollar reservoir because you're afraid that there is a 1 in 100 chance that it might fail? Look at it again. And then they bring the experts on the other side, and they will tell you, you should go ahead, there's no problem. And they start insulting you in a room when everything is being recorded, and it can get super, super hard.
So I don't have a question for you. I just want to have a very clear and certain, no uncertainty in this. It was the right decision to challenge you to be here. So it's good to have someone without gray hairs, at least dominating. Thank you, Zé Pedro, for accepting our challenge.
Thank you so much. It really means a lot.
Very, very short. Sorry. But, I think also we are partly a little bit... I think we have to think again, what is our role? And I don't think it is our role to tell politicians you have to do this or that, or you don't have to do this, or you don't have to do that. Politicians, policymakers, the society, they set actually objectives, they have goals. They actually say, we want to build a dam. The great advantage is we will have a lot of electricity or water reservoir. What is the risk? They will ask us, what is the risk there? And then we have to balance benefits and risks and communicate that message. I don't think it is our role to say, don't build the dam, because this will ultimately in 10,000 years kill many, many people. That's not our role. I think our role is really to advise policymakers by saying, if you do this, the consequence could be that with such a probability. And then it's up to them to decide what they make of that. Sorry.
Okay, that is very, very quick. Rodrigo, please.
Hello, Pedro. Thank you very much for the nice and wonderful presentation. My question is about to be practical, about the example that you gave in Kazakhstan dam. So you made that very complex analysis with all the risks. What was the practical result? So, there's another way. We were discussing about how hard is to make risk, how hard is to make a point that there's a slightly chance that something goes wrong. But then when someone asks you, how do you know? And you come on along and you present lots of graphs, lots of simulations, millions of simulations. It's very hard to communicate that that science to someone that has to make a decision. So my question is very practical on that specific example. What was the practical results and what kind of interaction that you had with the decision makers?
Okay, thank you for the comment and the question. I will link both and try to answer quickly. So, again, I fully agree with you. In projects in the European Union, in projects financed by the World Bank, it's easy to stop, or easier to stop. My state of mind is more related to projects in countries that have democratic in the name of the country, and where most of the dams are being built. And then the process is a little bit different. So in this specific case, what happens was that there was some delays in the project, as there are bound to be, and there was this inventive solution to save money and build faster in a very critical and risky phase of the project. And we did some calculations, and it was apparent to us that it was just too risky. So then we had some difficult discussions. We had our models, and finally we succeeded in searching for safer alternatives due to, among other things, this risk analysis. So it was a successful case. We, of course, brought in very reputable people because gray hair has a role in these things. If I'm saying to a project committee, oh, I really think it's too dangerous because I have a model, they will just laugh in my face. You need someone with a lot of experience. You need someone with a lot of gravitas that convinces people. This was a good outcome in this case because we really prevented this very dangerous solution to being attempted. Yeah.
Then I would like to thank both guest speakers for their engaging keynotes, and would like to start the roundtable by inviting the rest of my guests to join us on the stage, on the table, please. Okay. Next, I will introduce each one of the speakers that hasn't been yet introduced, and give each of them a 5-minute period to talk a little bit about important issues related to floods. So our first speaker will be Christian Stamm, and Christian studies biology at the University of Zurich and a PhD in soil physics at ETH Zurich. Since 2022, he works as senior scientist at the Swiss Federal Institute of Aquatic Science and Technology, IAWAG, and is nowadays the Deputy Director of IAWAG. So please feel free to present us your keynote.
Okay, now it seems to work. Okay, thanks. So first, thanks for the invitation and thanks for the opportunity to share a few thoughts from our side. I think there should be a slide with some ideas that we were asked to prepare. So some reflections from our side, and I'm representing IAWAG and let's say the expertise we have there. I will say more about that in the afternoon. So one thing I would to highlight at the very beginning, which is probably a little bit outside of what we discussed so far. Floods are not only threats to humans, which they are, but they are also necessary for maintaining healthy aquatic ecosystems. This tends to be forgotten sometimes, but if you are looking from an aquatic ecology point of view, they have an essential role to play. And I will show one example in the afternoon, but I think we should not tend to forget that completely. So one aspect that was alluded to already, but I would like to reiterate, is that the kind of challenge how to create a water management across different spatial scales. So we have seen very nice examples before in the presentation on the dam. So we need to think about the dam, but there's the downstream area as well that might be impacted, not only in cases of dam failures, but if you talk about floods, where do they originate from? Where do we implement measures for retaining water, for example, to mitigate flood damage? We need to consider the different scales at which decisions are taken, and to come up with, I think, sustainable and viable solutions. We need long-term inter- and transdisciplinary collaborations between research and the stakeholders. So this goes very much into what we just discussed about how to communicate also risks. So if you would like to be able to do that, you need to have kind of established channels between different groups, stakeholders, where there's also trust and where you can convey this kind of information. And I fully support the aspect that was mentioned before as well. You need to think about how to decide beforehand. I mean, if you need to decide on the spot, this should not be the case how to handle floods. And I think that's for the moment.
Okay, thank you, Christian. So we can move to the key points of Elsa. Elsa is a civil engineering and has a Master of Science in Water Resources and Hydraulics, and also a PhD in Civil Engineering. She works as a researcher at LNEC in the Water Resources and Hydraulic Structures Division. So please.
So, good morning. First, I would like to thank to my LNEC colleagues for this invitation. It's a pleasure to be here. So I work in the Water Resources Division and Hydraulic Structures, the same division as Teresa. And in our activity, we need to model or estimate floods in rivers. So, floods in rivers are triggered by intense precipitations and also by other factors of the river basin, for instance, occupation, steepness of the slopes, and also for flood regulation in rivers. So we need to estimate these floods for what? For instance, to elaborate flood hazard maps, which are key instruments for flood risk management, disaster preparedness, and for instance, for the municipalities, for land use planning, especially in flood-prone areas. Additionally, we also need to estimate floods, to model floods, to design hydraulic structures such as dams and river works. So, since climate change are triggering influences the precipitation, how can we integrate these effects of climate change into flood estimation? That is the main key issue here. So you know that traditionally we tend to characterize floods based on the historical records. Records from precipitation, records from floods. However, usually the flood records are not so long. And we based our methodology on what we call EDF curves that relates the intensity of the precipitation with the duration and with the frequency. So, to include the effects of climate change, do we need to redefine these EDF curves? Do we need another approach to estimate the floods? What we need to know? This is a research area that has to move forward fast because, as we heard yesterday, we expect significant changes on the climate in this century. So, related to this question, do we need to review also the flood hazards maps that we use nowadays? Do we need to review the design of the hydraulic structures? Do we need to review our Portuguese law that frameworks the elaboration of the flood maps, as André spoke before? So, also connected with this question, rivers are not disconnected from the coasts. So, there are some areas where we can have floods from the coastal zone or floods from the rivers, or both. How to deal with those flood maps? Do we superimpose the flood maps, or do we try to define a scenario to define these flood maps that takes into account the climate change effects? Nowadays, for instance, the colleagues from the coastal area are including the sea level rise on this these flood inundation maps. But for us, from the river systems, we are not using those aspects. So this is a question that needs some research and, as I said before, some guidelines to produce new methodologies to tackle with the subject. Finally, I don't know who can switch the slide. It's okay, sorry. Sorry for this. So, another question that arises from our flood studies in our division is there are people who lives or works in flood-prone areas. And sometimes we perceive that those people are not aware of the flood risk they are exposed to. That problem comes from the fact that in our climates we do have some long periods without floods. So it seems that the flood problem sometimes doesn't exist or was solved or it is mitigated. So that raises the question that we need to raise public awareness of the role of the river and river-based interventions in reducing or not the flood exposure. I'm saying this because sometimes people living in those flood-prone areas benefit from flood protection measures. I'm speaking about flood flow regulation by dams or flood defenses. That doesn't ensure that you are not exposed to a flood. You are still living in the flood-prone area. You have to deal with the floods because flood regulation or flood management, it depends on the many factors. It depends on taking into account floods coming from different rivers, the possibility of impound the flood waters in the reservoir, the release of flood waters in time, not provoking a more intense flood. And also, when we look for flood defense, especially for dike systems are built with earth material. So when the river level rises and overtopped the dike, some breach can appear and a more intense flood can be produced in that area. So people should be aware that they live in the flood-prone area, although they have protection measures, but flood can appear, so these structures should be monitored, and some earlier warning systems also should be implemented. So I think I said my time.
Thank you, Elsa, for your very interesting key points. Now we can move to the next speaker, José Saldanha de Matos. He is full professor at the Instituto Superior Técnico of the University of Lisbon. He chairs the Hydraulics, Environment and Water Resources area of the Department of Civil Engineering, Architecture and Environment. Nowadays, he also is the president of the Portuguese Water Partnership.
Okay, thank you very much. At first, congratulate LNEC by this interesting, productive initiative, and all the ones that were involved, Helena, and Maria João Rosa, Maria do Céu, Elsa, and so on, colleagues at LNEC. Thank you very much. And of course, congratulate the keynotes. They were excellent. Well, after the complexity, after the uncertainty, some very simple, practical messages. The first message is that, in fact, you have this flooding in large rivers. It means after days and days of intense rainfalls, sometimes weeks. And you have another type of flooding that occurs in those peri-urban brooks, so in small, medium catchments of a couple of thousand of hectares. These are probably the most critical in terms of fatalities. In Portugal, you have been in the last century, in 6-7, an event like that, 700 people have died. And afterwards, in 83, also 10 people have died. And we have also these flash floods in the center of the city, where the catchments have concentration times of some minutes, 20 minutes, half an hour, things like that. And those last, in general, don't lead to fatalities, but very, very high losses. In the last, after a serious drought in the last year in Portugal, in December you have two events, two intense rainfall events, and just in December the losses were estimated in the city of Lisbon, just the city, in 4-8 million euros. So it means that this type of, the solutions for this type of events, of flooding, are completely different. And the causes are always the same. Of course, climate change, but the land use is very, very important. So it means the sealing, the improvements, and so on and so on. And looking to all these projects that I was involved, in general, you have 4 factors that leads to special problems. Flat areas with low gravitational potential to ensure runoff, flat areas. Areas don't seem large watersheds. When I say large watersheds, I'm speaking about in the context of urban, in urban areas. Intensely urbanized, of course, because when control land use, and areas close to the ocean or to estuaries because of the tide effect. It means that there are places like that where these factors are converged, in Lisbon, in Porto, in Setúbal, and so on, and in large of coastal cities in the world. So it means, and well, all equal, all different. In fact, being in developing countries, being in large cities, in medium cities, the challenges are more or less the same. The solutions may diverge, but the challenges are the same. And you combat this challenge always with the same type of approaches. Mitigation strategies, it means reducing peak flows, reducing the runoff by centralized solutions. It means source control that increase the retention and infiltration. But you have also, in a lot of situations, a need of adaptation strategies. It means that you assume these peak flows and you try to control it. Large sewers, tunnels, large storage, and you have different solutions for that. In general, for a city, you have the good solution, the best is the hybrid solution. It means combine mitigation strategies with adaptation strategies. And, well, there are some images. Of course, that there are tendencies in the world. I would say that one great challenge is the centralization. Small is beautiful, so it means trying to solve at source this problem. But of course, the hybrid solutions are the solution. So no, so just for ending, a message that in general, because of this uncertainty and because the investments are very, very, very high, you have the examples of here in Lisbon, you are constructing 2 large tunnels. The investment is about 140 million euros. And I was involved, I was the team leader of the Lisbon Drainage Master Plan, and I remember that in 2015 I had a lot of meetings with the mayor. The mayor is Medina. Medina is now the Minister of Finance, so it means that he's economist, so he gives a lot of value for the money. And after 3 or 4 meetings, well, there were no decision about to do things or not to do things. And I remember that I just, in the last one, I showed a video about the consequences. It was a 2D model, just that, but a video with the flows in the sewers and the flows outside the sewers in the surfaces, and the depth of the water in different parts of Lisbon. After that video, he decided. So it means that the communication is very, very, very important. Okay, thank you very much.
For these interesting points, so we can move to Maria do Céu Almeida. She is civil engineering and has a Master of Science in System Engineering and Operations Research, and also holds a PhD in Civil and Environmental Engineering. Nowadays, she is principal researcher at LNEC in the Urban Water System Division.
Thank you, Teresa. Good morning, everyone. Thank you so much for giving me the opportunity to be here and share some ideas with you. And trying to be as practical as possible. One thing that I think we are disregarding is that we have extensive knowledge, technical, scientific, and even talking about what José just said, the ability on what techniques are good for communicating this type of problematics and issues regarding risk. However, our systems, and I imagine that also in the universities, we are taught to use the same techniques that we used since at least mid-20th century, and we are not really putting forward all the new knowledge that we have at hand. In practice, of course. These kind of practices assume a certain level of risk acceptance. If we decide to design a sewer system with a return period of 10 years, that is relatively common, we are assuming that any rainfall that goes over it is going to bring problems. It's going to bring flooding. And we know that we have floods for so many years. If we talk about floodings in Portugal, we are used to them, right? So this is not a new problem. What is new is that that can happen much, much more frequently, and so our EDFs are not appropriate anymore also. So we need to look at our systems in a different way, to look into the water cycle, to adopt multidisciplinary approaches, and start to apply new paradigms. And I just wanted to mention about the Green Deal. It's a great idea to have a Green Deal in Europe, but perhaps we should also have a Blue Deal so we can work in a more integrated way also, because the directives and documents about water are quite dispersed, and we have some problems that we referred some of you yesterday. When talking about cities, the need for changing this paradigm includes, for instance, that the water management is done with territorial management, involving all the sectors. And even in cities like Lisbon that are densely stabilized, densely urbanized, we can make changes. We have to do changes. We must have space for water to flow when there is the capacity of the systems is reached. So we need to involve not only people from drainage department, but also to talk and involve the urban planning, the water supply systems, the public places management, and so forth. We have also to improve the coordination between different entities responsible for different services. And we can see we have had the opportunity to have some of these projects, European projects, where we were working with the energy supply, water supply, transportation systems here in Lisbon, and it is clear that there is a lack of interchange of knowledge. They do what they can from their side, but they do it in silos. So we have to help them to make common decisions and support their decision as much as possible. One other thing is that when we talk about floods or flooding risk and reduction measures, sometimes we act without investigating the root causes of, in each case, what is leading to the flood. We might have only a problem of the inlet components, and there is spare capacity in the sewers, or not. So we have to select the measures taking into account the causes to act effectively. And also, we build the systems, we design them, we are very happy with the design, but then the risk of failure generally in the several functions that these systems are built or should be prepared to, the system degrades and the risk of failure increases with time. And even knowing that, and of course they have a design life, typical 40 years, but they last much longer. The system of downtown Lisbon was built after Lisbon's earthquake, the main system. So it's far over 40 years design time. That was not, of course, used at the time. It's still working, not bad. What is missing? Is missing also to take seriously the tasks and resources for the people that have these tasks to do the maintenance, to rehabilitate the systems. So the effective systems management needs to increase the assets service life, and even in Europe we also have now a call about this. We need to look at the infrastructures that we have and upgrade them and not build new ones only. Of course there are situations where we have to build new ones, that is clear. But rehabilitate and reuse what is already underground. Underground and in the cold, it's not only underground systems, but very much that because they are not so visible. José already talked about the need of integration of surface systems with buried systems to have a transition to hybrid system. This is fundamental. That is one way of retaining and emphasizing and creating the old hydrological functions of drainage in the nature and reuse them and improve them in already stabilized city areas. Another problem that we have is we do not have good information. We don't know the flows, we don't know the water levels in most cases, or we don't know enough about it. So it is very important to invest also in monitoring, wood quality monitoring, and here another side of uncertainty is given where the uncertainty of measurement in open water flows is quite high. And so we need to have conditions for people working in the practice to make also better investments in that area. Finally, just final words, separating the waters is something that we should take seriously. We have the problem, and the new directive is putting some stress on managers on that, because we have many combined sewer systems, and we have very, very frequently, and we do not know how frequent we discharge and how much, because we don't have the information. And we need to take it seriously also in the parts where the systems are separate, because there are many wrong connections, inflows that should not be there, infiltration in large quantities, also because systems are degraded. And we need to deal with these even potential sources of water that we can use to face other problems like the scarcity of water. Thank you very much for your attention.
Thank you, Sue. So, as we have now a period of questions, and I will start saying that floods are likely to become more intense or frequent. And in Portugal, in the last 6 years, floods have cost, namely to municipalities, over 100 million euros. So we have solutions. We saw engineering solutions for increasing the resilience and safety of existing water structures, environmental friendly solutions for new technologies for monitoring and processing data, real-time monitoring and control, machine learning, early warning systems. We also have those non-physical measures, which include the very important aspect of a better water management and a better water governance. In this context, I would like the roundtable to address some key issues, namely how to predict floods, how to anticipate and be prepared, what are the future challenges, etc. So I will address the first question to José Pedro. You have shown us a very interesting case study in modeling, in advanced modeling. So I would ask you, what is the future of flood forecasting and management? Forecasting.
Thank you for the question. It's a very difficult question to answer. I think we could advance in mainly two ways. One would be to more and more base decisions on full knowledge, so integrating uncertainty. Consistently using these ROC curves, consistently transmitting full uncertainty and deciding upon it. This is one way of doing things, and we can do it right now. Also, more and more, I think artificial intelligence will be useful in this field. You of course, have experimented with ChatGPT, I'm sure. The same technology, the transformer technology or a deep neural network, the concept can be used in time series analysis. I've just tested this month one of these models. It's called the TFT, Temporal Fusion Transformer, and it just blew my mind. It really understands the processes: snow melt, temperature increase, rainfall. And in my experience, it's just much better than anything I'd used before. And it can, I have high hopes that it can bring information from neighboring catchments. So with it, like language, so ChatGPT speaks English, Portuguese, Armenian, whatever, because it blends information from different contexts into its predictive capability. And I really do hope that flood forecasting can use the same kind of information from different sources, different catchments, different climates, to improve overall prediction capacity.
Thank you, very interesting. Yeah.
Okay, thanks. I basically agree very much with that. I would like to point to one issue that bothers me a little bit. The big companies like Google, they invest in that. And they are the owner of data sets of global scale that are in their hands. And they are performing hydrological predictions with really unprecedented quality. So there's an issue about scientific progress and who owns the data, who has access to the methods, and can hence also control the output. And so that's not disqualifying, let's say, the potential that there is out there. But with big data and artificial intelligence, we need to think about who actually has the power to regulate also access to information. And this is, I think, especially in the context of flood warnings, whatever, if we have issues there that a few players can kind of determine who gets good predictions or not, I see that as something we need, especially in the academic world, but also with public authorities. We need to think about that also in the future.
That's a very important point, yeah. So we can continue. Let's see, Andrea. Right. What is the main challenge for the next coming years for coastal inundations, namely in Portugal?
Thank you for the question. I think my major concern is really sea level rise, because we, the authorities, are used to deal with flooding as a sporadic event and as a local event. This means that you may have flooding, say, in the north of Portugal, which have good weather in the south of Portugal, so that they can concentrate in one area. It also means that when you have a big flood, then you have time, you have years to address the problem, to rebuild the dikes and so on. With sea level rise, it won't be local and it won't be sporadic. So the authorities will have to deal with the problem in a different way. They won't have the luxury of time, and they won't have the luxury of addressing problems here and there. They'll have to address a problem that will cover the whole country, or at least the whole coast. So I think that will mean a change in the way the flood problems are addressed.
Okay, thank you. So perhaps linked to this matter, I can ask Elsa. Will river floods become more severe or more frequent in Portugal due to climate change?
Thank you for the question. So I think because flood processes are quite complex, they depend on the precipitation, but also depend on other factors, in land occupation, flow regulation. It's quite difficult for science to identify in the flood records a trend associated to climate change. So instead, science tried to look to the precipitation, especially to the precipitation with daily precipitation or sub-daily precipitation, and looking to the records of this series of daily precipitation, and also based on the results from climate model projections, it is already identified or it is expected an intensification of the intensity of precipitations and more frequent precipitations. One number comes in the research papers is that there will be an average of 7% of increase in precipitation per 1 degree Celsius of warming. So if the climate goes 1 degree in average warmer, then we can expect an increase of 7% in the precipitation. But the question is not so simple. This 7% can be higher for precipitations with longer return periods, and also it's not uniform along the planet. So it is also pointed that, sorry, I tried not to approach because of the noise, but maybe people are not hearing me. But this increase or decrease in the extreme precipitation, it depends on the time of the year, on the regional area. So there is no final conclusion yet. Still, I would like to say that in Europe we do have a flood directive that established the framework for river flood risk management plans, and the European Commission is recommending to the member states to include more and more the climate change effects on the magnitude and frequency of the floods. And the member states, some of them are including already that type of influence, but the methodology is still very different from country to country. So that's why I stress the need to come in the next years with some way to introduce these climate change effects on our methodology to estimate floods. But I think the conclusion could be we should expect more frequent and rapid floods in the future.
Thank you, Elsa. Christian, how can the South European countries as Portugal learn with northern countries in flood governance, namely in transnational rivers?
I think I'm not here to tell other people with other contexts what we could teach you. I think we can share experiences. I've learned a lot here over the last 1.5 days, so I'm thankful for that. I think we share in different contexts similar problems, and one thing is the upstream-downstream situation. So we have this within Switzerland because, for example, parts of the water management is done at the what we call cantonal level, so not at the national level. So there is the need for coordination between different cantons, which of course do not follow the boundaries of the watersheds. So and there are certain established ways of how to do that, and I think this is very important, and it has been partially successful also in the past to manage also serious flood conditions, because it's not just to protect one city. You can say, okay, we protect one city, but by discharging more water, because almost all lakes in Switzerland are regulated. There's one large lake which is not. The others are regulated. So we have the dams, of course, but we also have the lakes which are regulated. So you can control how much water you leave to the downstream, but then at some point you just move the problem from one location to the other. So there need to be a kind of a balance. And there we are. This is one aspect of the, let's say, conflicts of interests. It's about protecting different sites, but also different sectors. So, and these kind of procedures, how to deal with such situations, they need to be established beforehand. Otherwise, it will be very difficult or impossible to arrive at an optimal level of management in these kind of situations. And of course, and this alludes to what you also mentioned before, land management and planning is very essential in that part. That, for example, we have certain priorities that we say, okay, in case of flooding, we allow certain agricultural areas to be flooded to protect other infrastructure. And this was implemented over the last 20 years because of major floods in the 1990s. And it turned out to be very successful. So you can prevent certain aspects, but you need to have this kind of implementation beforehand. I think we also have, of course, a certain responsibility to the downstream countries like Italy, Germany, and so on. And especially in critical situations, if there's a lot of rain coming from the south towards the Alps, we have issues between Switzerland, protection of the Ticino area, and protection of the Po Valley. And there are kind of political issues that have not completely been solved, because Italy regulates the outflow of Lago Maggiore, and hence they have a strong handle on what is the flood level in Switzerland. So, yeah, I think at that point, the political issues come into play, and they need to be solved beforehand, otherwise it's really getting difficult. So I think we share experiences, but we don't have yet found the silver bullet, sorry.
Advanced preparation for a flood can save properties and life. So how can urban water infrastructures be more resilient?
Thank you, Teresa. I think what we need to be resilient, our cities are the areas that have values that we want to protect. And of course, the barrier systems are important, and we have a lot to do to improve their functioning, even not building so much. In terms of areas, I think I remember that when I was in Switzerland, I read that there is a system there, but you correct me if I'm wrong, where new developments had to show that they managed the flow to a level of not letting more the natural situation downstream in terms of volume of water. I think that's correct, yeah? Before the development. And this is a good example we can learn with Switzerland on things that we can do. But anyway, we have, of course, like Miranda was saying yesterday, we have to be prepared to avoid, at some level, the events of flooding, but they will happen anyway, and we have to be prepared to teach all the actors to reduce their vulnerability. And being the populations, the business owners, even help the municipalities as research institutions to develop new ideas and analyze the problems that have solutions, or the solutions that can be compared. So, and the politics, or let's call it the policy and the regulations need also to be changed in order to people acting in practice be able to be more effective and do what they wish to do, and sometimes they do not have the resources.
Thank you very much. And I think we are getting a little bit out of time, but I should like to address a final question to José. So our cities, our Portugal cities, prepared for floods, namely concerning the urban stormwater.
Yeah. Okay. The day before yesterday, I received a note by the European Policy Committee of the European Water Association, I remember, saying, yesterday, the European Parliament has adopted the new wastewater treatment directive. And now initiates the dialogue between the Parliament, the Council, and the Commission. It means that in 4 or 5 months, we will have a new directive. And I think that you are a little bit anesthetized, because this new directive will have an impact in the sector. It's like an earthquake. There are things like the energy neutrality in the treatment plants. There are things like the quaternary treatment in large treatment plants. But it's also related with rainfall, because one of the big challenges, and you are not prepared for that at all, is to control the loads of the overflows. And I'm not speaking about just combined systems. I'm speaking also about separate stormwater systems. To control this in terms of flows obliges to monitor the quantity and to monitor the quality. And the target is that from overflows, the loads will not be higher than 1% of the total urban load for the receiving water. So it means, well, you should begin from almost the zero to monitor overflows, to monitor direct discharges in the receiving water, with the uncertainty, the variability of the flows, and the variability of the pollutant concentrations. So my simple question is, who will fund the necessary research, planning, and implementation? It's something completely new. Okay, thank you.
Thank you very much. We are completely out of time, so if you have any question, please, you can talk with our guests directly in the coffee time. So to finish, I would like to thank all our guests for their engaging contribution and close this section. So please.
So before you leave, for those of you who were not yesterday evening, so first thing you missed a very good music at the end and a good party. So the municipality of Lisbon very kindly printed the posters of the conference. This was made by an artist by Oporto that can design the logo and the topic of the theme. So you can take, if you haven't done that yet, please collect your poster at the reception. And please, we are going to shrink the break in order to resume the right timetable of the program. So you'll be here at 12:30. Thank you.